Picture this. You have just landed at LAX. You are completely exhausted, just dragging your suitcase through those endless, fluorescent hallways of the terminal.
Oh, yeah, the worst part of the trip.
Exactly. And you finally step out into that chaotic, smoggy Los Angeles air. You open your phone, you tap a button to request a ride, and you just watch that little loading spinner go around.
Just waiting for the magic to happen.
Right. And within seconds, your screen flashes. A specific driver in a specific car is assigned to you. But, and this is the crazy part, if you actually stop to look around that airport, there are hundreds of cars circled.
Hundreds, yeah.
There's a massive holding lot literally miles away packed with drivers. So how, in those 2 or 3 seconds, did the system pick that specific driver out of the hundreds waiting in the lot to come pick you up?
I mean, it feels incredibly seamless on the surface, right?
Yeah.
But underneath that little loading spinner is honestly one of the most intense, high-stakes mathematical puzzles happening in real time.
Yeah.
What you are experiencing in that exact moment isn't just like a basic search function. It is a massive system design and operations research problem.
And that is exactly our mission for this deep dive. We are opening the hood on the actual algorithms that run Uber's dispatch engine for auto dispatch, or DIP for short.
Yeah.
We are going to decode how engineers solve this massive high-speed puzzle of matching drivers to riders in real time. We have a stack of sources today that break down the exact mathematical models, the algorithms, and, crucially, the real-world compromises required to make these pairings happen at a place like LAX.
Which is, one of the largest global pickup hubs on the planet. And this isn't just some hypothetical whiteboard exercise either.
Right.
This is the literal architecture of how modern transportation networks function.
Yeah.
So the sources we are looking at pull back the curtain on how a platform balances the competing needs of the rider, the driver, and, well, the system as a whole.
All in the blink of an eye.
Exactly.
Yeah.
All in milliseconds.
Okay, let's unpack this. Because in my head, organizing an airport like LAX should be, I don't know, fairly straightforward.
You'd think so.
Right. Like there is a physical staging area, the TNC lot, where drivers wait. The app should just work like a deli counter. I pull ticket number 1, I get the driver who has been waiting the longest, or maybe just the one closest to my terminal. It's just a simple distance calculation.
Yeah, I mean, it seems like it should be a simple one-to-one queue, but that kind of localized thinking would literally cause the entire airport system to collapse.
Wait, really? Collapse?
Oh, absolutely. So the system does honor a virtual queue for drivers, right? Giving general priority to those who have waited the longest.
Right.
But the system does not match riders and drivers one by one as they click request.
Oh, interesting. So it's not instantaneous.
No, not at all. Instead, it relies on a concept called batch dispatch. Every, say, 2 to 5 seconds, the system essentially pauses.
Yep.
It gathers all the requests from riders and looks at the entire pool of available drivers, and it makes a batch decision for the whole group at once.
Let me push back on that for a second. If I hit the button and there are 50 cars right there, making me wait an extra 5 seconds just to be bundled with other people feels, well, incredibly inefficient. Why not just match me instantly?
Because an instant match might be good for you, but disastrous for the network overall. Let's look at the core problem laid out in our sources. We can call it the 100 by 100 problem.
Okay, I'm tracking.
Imagine there are 100 drivers in that virtual queue, and in your specific 5-second batch window, 100 trip requests arrive simultaneously from all the different LAX terminals.
Which at LAX is very realistic.
Very realistic. The system has to calculate an expected value for every single possible pairing. Driver A to rider 1, driver A to rider 2, all the way down the list.
Okay, so a 100 by 100 grid means the system is evaluating, what, 10,000 possible combinations in that tiny 5-second window?
Exactly 10,000, yeah.
But what exactly is expected value? Are we just talking about the price of the fare?
It's a bit more complex than that. It is a specific mathematical formula. We'll call this value C sub I.
C sub I, got it.
It equals the expected financial earnings of the trip minus the penalty for what the industry calls deadhead.
Deadhead being the empty driving time, right?
Right, the time it takes the driver to actually get to the passenger. And then you also subtract the penalty for how long the rider has to wait. So the ultimate goal of the dispatch engine is to maximize the total combined value of all 100 matches it is about to make simultaneously.
Wait. So the system is actively choosing not to give the first rider the absolute closest driver if holding out makes the overall group of 100 riders better off.
That's exactly right.
That sounds like a utilitarian nightmare if you happen to be rider number 1. I mean, you could have had the car right in front of you, but the system decides you have to wait an extra minute so that rider number 12 isn't stranded for 20 minutes?
It is a bit of a nightmare for Rider 1,
Mm.
but mathematically it is necessary. If it just gave Rider 1 the closest car, it might accidentally assign the only driver who has a child seat, or, the only extra large vehicle, to a single person with a briefcase.
Oh, wow. Yeah, I didn't even think about vehicle types.
Exactly. That completely ruins the match for a family of 6 who hits a request half a second later. Batching prevents those deeply suboptimal local decisions by forcing the computer to look at the global picture.
Okay, conceptually, I understand wanting to maximize the happiness of the whole group, but what does this all mean for the engineers writing the code? If you map this out mathematically, how do you prevent the computer from coming up with impossible solutions?
What do you mean by impossible solutions?
Well, because if a computer's only goal is to maximize a numerical score, it's going to find loopholes, right? Continuous math does weird things.
Ah, yes. You've hit on the central engineering challenge. This brings us to the formal mathematical name for this scenario, the bipartite assignment matching problem.
Bipartite, meaning two distinct parts. Drivers on one side, riders on the other.
Precisely. You draw a bipartite graph. On left side, your 100 drivers. On the right side, your 100 trips. You draw lines connecting every driver to every trip, and every line has that expected value we just talked about attached to it.
The C sub I value.
Right. The objective is to find the maximum weight matching. You need to select exactly 100 lines that connect everyone uniquely, yielding the highest possible total score. And as you pointed out, if you just feed this pure calculus into a standard algorithm, the computer will do what continuous math does. It will output fractions.
Right. Because a continuous curve finds the absolute mathematical peak. The computer looks at the grid and says, well, to maximize efficiency, send 60% of driver A to terminal 1 and 40% of driver A to terminal 2.
Which is physically impossible.
Yeah, you can't chop a Prius in half.
Exactly.
Yeah.
Normally, to force a computer to only give whole number answers, one driver, one trip, you have to use what's called an integer programming solver. You're locking the math down, telling it to only check integers.
Makes sense.
But integer programming requires immense computational power. It has to check combinations one by one, which is way too slow for a 2-second batch window.
Yeah.
But what's fascinating here is the mathematical cheat code our sources reveal.
Oh, a cheat code. I love that. What is it?
The incidence matrix of a bipartite graph naturally forms something called a totally unimodular matrix, or a TU matrix.
Oh, totally unimodular matrix. Okay. How does a TU matrix solve the fractional Prius problem?
Think of it this way. Because of the specific constrained way a bipartite graph is structured, every connection goes exactly from one distinct group to another, with no internal cross-connections. The mathematical grid representing it has incredibly rigid properties.
Okay.
It allows engineers to completely skip the slow integer programming solver. Instead, they could use a much faster linear programming relaxation, which normally produces those messy fractions. But because the matrix is TU, the underlying geometry of the math is physically restricted from settling on a fraction.
Oh, I see. So instead of standard math, which acts like a rubber band that can stretch and settle anywhere on a continuous line,
Yes.
the TU matrix turns the math into a pegboard. The strings can only be stretched between predefined holes. It's physically impossible for the algorithm to land halfway between two pegs, so it naturally snaps to a perfectly whole number every single time.
That is a perfect analogy. The simplex algorithm runs at lightning speed, assuming it can use fractions, but the pegboard nature of the TU matrix forces it to naturally stop right on a whole number integer solution. You get the speed of linear programming with the precision of integer programming.
That is wild. It's like trying to divide a pizza among friends and using a math formula that magically guarantees every single slice comes out perfectly intact. No messy fractions or crumbs to clean up.
Exactly. It's brilliant.
But knowing the math guarantees a whole number is one thing. Actually executing it at scale is another. If we are talking about an entire city instead of just LAX, checking every combination on a massive pegboard must hit a computational wall eventually, right? Is a basic LP solver actually fast enough?
It does hit a wall, and this is why engineers don't just rely on one algorithm. They use different algorithms based on the scale of the problem.
Okay, so they switch it up.
Right. For a small 100 by 100 grid at LAX, they use the Hungarian algorithm, or sometimes an optimized version called Jonker-Volgenet. It's incredibly precise and solves the puzzle in about 1 millisecond.
1 millisecond. Wow.
But the Hungarian algorithm has a complexity of O(n)^3, meaning as the pool of drivers grows, The time it takes to solve grows exponentially. It works flawlessly for up to about 10,000 requests.
But on a Friday night across all of Los Angeles, you could easily have 100,000 requests. At that scale, if the time it takes grows exponentially, a single batch calculation could take minutes instead of milliseconds.
And no one wants to wait minutes.
Right. So here's where it gets really interesting. What is the alternative to the Hungarian algorithm?
When dealing with distributed systems across a whole city, engineers often shift to something called the auction algorithm. Instead of trying to solve the entire pegboard at once from a top-down perspective, the algorithm essentially holds a microsecond auction.
Wait, does that mean the computer is literally holding a microsecond auction where virtual versions of drivers bid on trips? Who is bidding on what?
It literally mimics a free market economy. The trips are the items up for sale, and the virtual representations of the drivers are the bidders. The currency they use to bid is their expected value, that formula of fare minus deadhead minus wait time.
Okay.
Let's say driver A and driver B both want trip 1 because it's a lucrative airport run. In round 1, they both submit bids. The algorithm acts as the auctioneer, sees the conflict, and artificially raises the price of trip 1.
Ah, so as the price of trip 1 goes up, the net profit for the drivers goes down.
Exactly. Eventually, the price of trip 1 gets so high that driver B looks at their virtual wallet, realizes trip 2 down the street is now a better deal, and shifts their bid.
That is fascinating.
The algorithm iterates through these micro-bidding wars, raising prices until every single trip is sold to a unique driver and the market clears perfectly. Because this can be calculated in parallel across multiple servers, it handles massive citywide scales much better than the top-down Hungarian method.
I love that. The app is running a silent, invisible Wall Street trading floor every 2 seconds.
That's exactly what it is.
But here is my concern with all of this pure math. Whether it's the Hungarian algorithm or an invisible auction, algorithms assume perfect compliance. They assume everything goes exactly as the math dictates.
Right, which it never does.
Right. Reality is messy. First off, latency. If the system has a strict latency budget of under 100 milliseconds to do this math, they can't possibly calculate 10,000 combinations from absolute scratch every 2 seconds. They must be cutting corners or recycling data.
You're exactly right. They are recycling data. This crosses from pure theoretical math into production engineering. Engineers use a trick called a warm start.
A warm start.
Yeah. When the batch window closes and the algorithm runs, it doesn't start with a blank slate. It takes the mathematical leftovers, specifically something called the dual variable from the previous batch 2 seconds ago as its starting point.
Because the state of the airport queue hasn't drastically changed in 2 seconds, driver A is still roughly in the same spot. That's incredibly clever. But what about the human element? The math assumes a driver accepts the trip. What happens when a driver simply declines a ride because they, don't want to deal with Hollywood traffic?
That phenomenon is called stochastic acceptance. To handle human unpredictability, the system doesn't just calculate the raw base value of a match. It takes that value and multiplies it by a probability of acceptance.
Oh, wow. So they use ML for that.
Yes. Engineers use machine learning models that analyze historical data, driver habits, time of day, and trip features to estimate the likelihood of a yes or a no.
So a highly lucrative trip that a driver is only 10% likely to accept gets severely downgraded in the algorithm's eyes, so the system doesn't waste time offering it to them.
Spot on.
Okay, what about a mismatch in raw numbers? What if a delayed flight lands and suddenly there are 150 riders, but only 100 drivers? You said earlier that the TU matrix and the bipartite graph require a perfect one-to-one grid to work.
They do. And if the numbers are unequal, the system solves it by injecting dummy nodes into the math. In your scenario, the system literally creates 50 ghost drivers to balance the equation perfectly at 150 by 150.
It's like inviting imaginary friends to a dinner party just so the seating chart works out mathematically.
That's a great way to put it.
But if a real rider gets assigned to a ghost driver, nobody comes to pick them up. How does the system prevent the algorithm from prioritizing these imaginary nodes?
By using massive financial penalties, the algorithm assigns a colossal negative cost to the ghost drivers. In the invisible auction, these ghost drivers are basically radioactive.
Okay, so the algorithm is mathematically terrified of touching them.
Exactly. It will exhaust every possible combination of real drivers first. It only assigns a ghost driver to a trip when it has absolutely 0 real cars left. When that happens, the rider matched to the ghost simply gets pushed into the next batch window to try again.
But wait, if drivers can reject rides based on probabilities, and sometimes riders get matched with radioactive ghost drivers, What if a rider expects 100% certainty of a ride? Can you actually mathematically guarantee a pickup in a system built on stochastic probabilities?
Guaranteeing it requires a massive leap in mathematical complexity. The sources note that to ensure, say, 95% certainty, you have to move beyond basic linear programming and use chance-constrained, scenario-based stochastic programming.
Okay, rather than just brushing past that mouthful of jargon, what does that actually mean functionally for the algorithm?
Functionally, it means the system stops just solving for what is happening right now. Instead, it simulates thousands of parallel universes of what might happen in the next 10 seconds.
Wait, really? Parallel universes?
Mathematically speaking, yes.
Yeah.
It asks, if I make this match and the driver rejects it, what is the backup plan? And if the driver rejects it, what then? It evaluates all these branching probability trees simultaneously and picks the initial assignment path that leads to a successful pickup in 95% of the simulated futures.
That is an immense amount of computation. I mean, my phone struggles to load a heavy web page sometimes.
Yeah, the server infrastructure is massive.
But I imagine they aren't just optimizing for speed and certainty. If the algorithm is tracking driver history, they must be managing the driver's livelihoods as well, right?
Absolutely. The objective isn't just raw platform efficiency. They factor in driver fairness. They track long-term earnings to make sure the algorithm isn't inadvertently starving one driver of good trips while rewarding another simply because of where they happen to park.
Oh, that makes sense.
To do this, they use a Gini coefficient.
Like the metric economists use to measure wealth inequality in a country.
Exactly that metric. They apply the Gini coefficient to track earnings equality in the airport parking lot. Mathematically, adding that variance penalty for fairness turns the linear programming problem into a quadratic programming problem.
Right.
It forces the algorithm to sacrifice a perfectly efficient route today if it means balancing out a driver's historical earnings deficit from yesterday.
The layers of variables here are staggering. But I am realizing there is a fundamental flaw in this entire architecture.
Well, what's that?
All of this brilliance, the TU matrix, the invisible auction, the parallel universe simulations, it entirely assumes you have the luxury of waiting those 2 to 5 seconds to batch the requests.
Right.
What if a different platform or a specific service tier doesn't have that luxury? What if riders arrive sequentially and the app is designed to give an instant, immediate answer the millisecond you hit request?
When you remove the batch window, you throw the pegboard in the auctions right out the window. You enter the realm of online bipartite matching. Online, in this context, meaning sequential. When you can't see the whole board, you face a massive dilemma.
If I can't wait 5 seconds to see who else requests a ride, the most obvious solution is the greedy algorithm. A rider requests a trip, you instantly assign the closest available driver.
Right. But mathematically, a pure greedy algorithm has a competitive ratio of exactly 1/2. A competitive ratio is a way of grading an algorithm against perfection. A ratio of 1/2 means that over time, the greedy instant matching will only achieve 50% of the optimal efficiency that a batch system would have found.
Leaving half your efficiency on the table is catastrophic for a business. Why is the greedy algorithm so bad?
Let's walk through a micro scenario. Imagine a street with 2 riders, A and B, and 2 drivers, X and Y.
Okay, tracking.
Rider A requests the car first. They happen to be exactly equal distance from both driver X and driver Y. The greedy algorithm just arbitrarily grabs the first one it sees, so it assigns driver X to rider A. A millisecond later, rider B requests the car. But rider B is standing right next to where driver X used to be, and is miles away from driver Y.
Oh, I see the trap. Because the greedy algorithm made an arbitrary localized choice for rider A, it completely stranded rider B. If it had just given driver Y to rider A, both riders would have had short wait times. You basically trap yourself in a worst-case scenario. Surely there is a way to beat the greedy algorithm and avoid that trap without batching.
There is. To beat the 50% ratio, engineers use the ranking algorithm. This was developed by Karp, Vazirani, and Vazirani back in 1990.
Oh, an old-school algorithm.
Classic computer science. The brilliance of the ranking algorithm is how it fixes the greedy trap. It introduces a carefully calculated element of randomness to its assignments before the matching even begins.
Wait, how does injecting randomness into a math problem make it more efficient?
Instead of just arbitrarily picking a driver based on distance, the ranking algorithm assigns a random hidden priority score to every driver the moment they log on. So in our scenario, when rider A requests a car and is equidistant to both X and Y, the algorithm doesn't guess.
It looks at the random hierarchy.
Exactly. If driver Y was randomly assigned a higher priority, the algorithm assigns Y to A.
By establishing a random hierarchy up front, it breaks the symmetry. It prevents an adversary or just really bad luck from perfectly arranging requests to force the algorithm into making the worst possible choice every single time.
Precisely. That upfront randomness guarantees that, over time, the algorithm won't get stuck in those localized worst-case traps. By doing this, ranking achieves an optimal competitive ratio of 1 minus 1 over E, which translates to approximately 0.63, or 63%.
So even with the most brilliant 1990s randomized algorithms, acting instantly means the platform leaves almost 40% of the potential optimal efficiency on the table compared to just making people wait a few seconds for a batch.
Yes, it is a massive trade-off.
That really puts that 5-second finding your driver loading screen into perspective. It is literally buying the network 40% more efficiency.
It's the trade-off that defines the entire user experience. And just a quick note for any software engineers listening who want to actually test their skills on this exact logic.
Oh, please.
The sources point out that LeetCode problem 1057, called Campus Bikes, is essentially the toy version of this exact D-ape architecture. It's the perfect way to practice everything we've just discussed about bipartite matching.
That's a phenomenal resource. So to pull all of this together, the next time you are standing on the curb at LAX, exhausted, tapping that request button, know that beneath that little loading spinner is an entire universe of operations research.
Literal universe.
You have a totally unimodular pegboard snapping fractions into whole numbers in milliseconds. You have invisible auctions fighting against strict latency budgets, machine learning models predicting parallel universes of human rejection, and ghost drivers balancing out the matrix.
It's wild when you list it all out like that.
It is. And on top of it all, the app is actively balancing your personal wait time against a global Gini fairness coefficient to ensure drivers aren't starved of income.
And, if we connect this to the bigger picture, the mathematical frameworks we just walked through aren't just for ride sharing. These exact same bipartite matching principles, the TU matrices, the online ranking algorithms, they govern how internet packets are dynamically routed through global servers to avoid bottlenecks.
Oh, wow. I didn't even think about the internet routing.
Yeah. They also dictate how organ donors are optimally matched with patients in hospitals, where both time and compatibility are absolutely critical. Once you understand the mechanics of the assignment problem, you are equipped to see these hidden, high-speed pairings happening all around you.
It really does change how you see the structural systems of the world. And it brings up one final thought for you to mull over as we wrap up this deep dive. Well, if the algorithm is constantly balancing your exact wait time against a driver's historical fairness rating and the platform's global revenue matrix, next time your driver is mysteriously 5 minutes further away than the car you can literally see parked across the street, ask yourself whose exact mathematical objective was your extra wait time sacrificed for.